Hey everyone, my name is Fidel Zea. I'm doing this pencast for Dr. Bailey's Physics 6C class at UC Santa Cruz. Today I'm going to be doing problem 58, which says, I'm going to let y'all read it for yourself, which says two 5.8 gram point charges on a 1 meter long thread on 1 meter long threads repel each other after being charged to 100 nanocoulombs as shown in figure 25.58. What is the angle theta? You can assume that the angle theta is a small one. Now, given the diagram, given the figure, we can safely assume certain things about this problem. But in the meantime, I'm going to stop the video for a second so y'all can try to figure out the given values in which we will use later on. I also want to apologize in advance for my voice sounding kind of raspy. I'm a little sick right now, but I'm powering through this. So, first things first, we're given that the length of both strings is L, which is 1.1 meter, and the mass of each point charge is 5 grams. With that information, we're also given that the charge for each being 1 and 2 is equal to 100 nanocoulombs. We're trying to find the angle theta in between both point charges here and here. But first, before we can get to that, there's another thing that we have to, there's another variable in the problem that we have to go through so we can get theta. And that is T, which is tension. Now, it's a pretty simple concept so long as you know what you're doing, but I'm going to take my time trying to explain it. So, first things first, I know there's a diagram right here that explains the point charge, but I'm going to make my own so we can understand it a little bit further. Let's say that this is the point charge, right? And this is the string that connects it. We're going to have a couple forces acting on that point charge. First one being tension, T, going in that direction, as well as gravity, which is mass times gravity, which is the force of gravity, which is mass times gravity. And then we have about 3 more forces acting on it. One being the force of the electron point charge pushing against the other point charge going in the x direction, as well as tension going in the x direction. Now, I'm going to explain it, but first I'm going to write it down first. So, T sine theta is the force of tension in the x direction, and T cosine theta is the force of tension in the y direction. The reason we can explain this is if we were to pretend that there was these triangles here, we could imagine that SOHCAHTOA sine that tension in the x direction would be opposite hypotenuse here, opposite hypotenuse, and then cosine would be adjacent hypotenuse. So that's how we get tangent cosine theta, and then not tangent cosine, tension cosine theta, tension sine theta. So this diagram helps explain how we got these representations of the value of tension. Now, another thing that we can break down even further is tension cosine theta. So, because it is pointing directly up, it is the equal and opposite force of gravity. So we all know that force of gravity equals mass times gravity, so we can easily just set it up like this. Another thing that we can go through is because the tension sine theta in the x direction is going to the left, and the force of the repulsion between the 2 point charges is going to the right, we can also set up t sine theta equals f of e. Now, this allows us to set up another equation when simplifying for tension. So if you were to move these values to the other side of the equation, we will get tension equals mass times gravity all over cosine theta, as well as force of electrons sine theta equals tension. Now, I'm going to give you a little break just so you can try and understand it for yourselves. There's some beeping noise in the background. I apologize about that. Okay, so where I was going with that was that the force of electrons, right? One of the major equations we're going to be using for the force of electrons is going to be the point charge equation, which is K constant, charge 1, absolute value, charge 2, absolute value, all over radius squared. So because we have that here and we have the equation, we can simplify it even further by plugging it into the tension equation that we built. So we're going to end up getting tension equals K charge squared all over sine, which basically just simplifies to sine theta times the equation. Now, because this is tension and this is also tension, we can set them all equal to each other and get the simplified version of the equation, which is, let me just double check to make sure that's in the view. Yeah, that's in view. All right, that's going to end up looking like this. Mass times gravity sine theta cosine theta is equal to K constant, charge 1, charge 2, all over r squared. Now, what this lets us do is we can even simplify it further. Sine over cosine is tangent theta, tangent. So we can simplify that by saying mass times gravity equals sine over cosine tangent theta K Q1 Q2 r squared, absolute values. Now, when we try to solve for theta, there's another predicament that we have to go through, and that is, what is the length of the arc in between these 2 point charges? So the relationship of the radius as well as the arc length and the angle. So L, which is our arc length, radius, which is our L, and then we have theta, which is our angle. This is the arc length equation. Now, because theta is small, because it's given to us in the equation here, we can substitute sine theta for theta, which gives us arc length equals L sine theta. Now, because we have 2 of these angles here, we're not just going to be using L, arc length equals L sine theta. We're going to be using the radius of the 2 angles of theta, which is going to be 2L sine theta. Now, this is a pretty important part because this R value is the one that we're going to be using for this value here. So when we go about trying to solve the equation, not only do we use it, but we replace it in the main equation that we made for ourselves. This is where we wanted to get to. I'm sorry I couldn't show it earlier on in the video. What we did is we moved mass times gravity over here, and so that divided out, and so we're moving all variables of theta over to the left, and then we're getting sine squared theta, tangent theta equals k constant, charge 1, charge 2, absolute value, all over 4L squared, mass times gravity. Okay, so this is what all the workup has been leading to, right? This equation right here. Now, because we have such small angles, we're gonna have to simplify and substitute tangent theta for sine theta. The reason we're substituting tangent theta for sine theta is because the given value of cosine theta is small enough to ignore in the equation given in the initial part of the equation relative to sine theta, yes. Now, first things first, we're going to be converting our charge values, Q, which is 100 nanocoulombs, to coulombs. The reason is because we want to use the SI values of it. So 100 nanocoulombs is the same as sorry, let me just do the math first. I can't do that off the top of my head. 100 nanocoulombs is the same as 1.0 times 10 to the negative 7 coulombs. Our mass, which is in grams, we're going to be using kilograms instead. So 5 grams, multiply that times 1,000 kilograms, negative 1,000 kilograms, is equal to 5 times 10 to the negative 3 kilograms. So these are the values we're going to be using for ourselves. The reason why is because they're SI units and they're simpler to use in the equation. The reason why is because if we just plug them into the equation straight up, we're going to have to convert in the middle of the equation, which becomes really messy, and we really don't want to deal with that. So here's the final part of our problem, which is sine cubed theta is equal to k, absolute value, charge 1, absolute value, charge 2, all over 4L squared, mass times gravity, given that our values are Q equals 1.0 times 10 to the negative 7 coulombs, mass, which is 5.0 times 10 to the negative 3 kilograms, and finally L, which is 1 meter. Given all those values, also gravity, 9.8 times 10 to the meters second squared. So that's everything that we've been given, except for K. Sorry, I keep forgetting things. 100. No. 9.0 times 10 to the 9th newtons times mass squared, all over coulombs squared. These are the SI units that we wanted: coulombs, kilograms, newtons for kilogram meters, second squared. Sorry, right there, second squared. Now we basically just plug and chug. I'm going to stop the video for a second just because I can write it down a little bit faster without recording. Okay, so it simplifies all the way down to that. And if you're wondering where all my units went, they all canceled out. So kilogram, coulombs, seconds, meters, everything cancels out, which is nice. Actually pretty neat considering how difficult this equation is. So the next step is we have to cube root the equation. Why? Because we have a sine cube. And so to simplify it to just sine theta, we have to simplify it further beyond that. It's just basic math. Plug it into your calculator. It's not too difficult. So that gives us sine theta. And from there, because we have 7.7 times 10 to the negative 3, we do the inverse, which is sine negative 1, sine negative 1. So we end up getting theta sine negative 1, 7.7 times 10 negative 3. And then we plug this all in to our handy dandy calculator. We end up getting a value of 4.4. And that is the problem.